It's funny. When most of us use an AI chatbot today, it feels just entirely frictionless, ethereal almost.
Right.
Like you open a browser, you type a prompt, and a second later, magic text appears on the screen. It just feels like the answer is being plucked out of thin air.
Whoa, I mean, it's deliberately designed to feel weightless like that. The entire tech industry has spent the last, 15 years training us to believe that the cloud is literally just a cloud.
Exactly.
Yeah.
But then you start actually looking into what it takes to make that magic happen, and suddenly that whole ethereal illusion just completely evaporates.
Absolutely.
You realize that what we call the cloud is actually a massive, roaring, heat-generating warehouse full of bare metal and incredibly complex plumbing and just a dizzying amount of electrical engineering.
It is the absolute definition of heavy industry. We've just disguised it as lightweight software.
Yeah, and that heavy industry is exactly what we are getting into today. We are taking a deep dive into the absolute engine room of the modern AI boom.
Right.
We've been poring over these internal blueprints, these architectural masterclasses and technical schematics of how the underlying infrastructure actually gets built.
Yeah, it's fascinating stuff.
It really is. Specifically, we're looking closely at the infrastructure blueprints from Supermicro, and they call it their SuperCloud Developer Console, which I think was previously known in the industry as SDX.
Right, SDX. And what we're really looking at here is the blueprint for a neocloud or GPU tenant cloud.
Okay.
And what's so fascinating about this material is just the sheer level of granularity.
Yeah.
Like, this isn't marketing fluff about synergy and, AI-driven workflows.
Right. None of that corporate speak.
Exactly. We are looking at the exact IT topology. We're going from the absolute bare metal, configuring layer 3 switches and NVMe storage pools,
Wow.
all the way up the stack to that magical one-click deployment of an AI chatbot.
So it's a massive, massive undertaking. So our mission for this deep dive is to translate that incredibly dense, highly technical map into a clear conceptual picture of how an AI factory operates. Whether you're an IT professional who is actually staring down the barrel of deploying this kind of scalable infrastructure, or you're just insanely curious about what physical actions occur when you query a large language model.
Yeah.
We are going to connect the dots between the physical silicon and the cloud-native software.
And to do that properly, I think we have to start by zooming out a bit.
Okay, let's do it.
Because the sheer scale of the tech world's pivot toward AI infrastructure right now is staggering.
Yeah.
We are fundamentally having to rip up and replace the legacy IT paradigms that the entire internet has relied on for the last 2 decades.
Okay, let's unpack that shift, because the legacy paradigm was basically a fixed ratio, right?
Right.
Like, you were building a data center 10 years ago, you bought a server rack, and it had a predictable amount of compute power, a predictable amount of storage, and predictable network bandwidth. It was essentially just a standardized box.
Precisely. It was a one-size-fits-all horizontal scaling approach. You need more internet, you buy more of those identical boxes.
Right.
But the AI revolution has completely shattered that mathematical model. The sheer hunger of GPU-powered supercomputers demands an entirely different approach to architecture.
Because they just consume so much more.
Exactly. We are transitioning from the data center to the AI factory. And in an AI factory, the management software has to be deeply vertically integrated with the physical hardware.
I see.
You are fighting entirely new battles now, specifically around power usage effectiveness, or your PUE, and thermal optimization.
Because GPUs run hot, really hot.
Oh, unbelievably hot.
You can't just slide an NVIDIA H100 into a standard server rack and treat it like a file server.
No, absolutely not.
It will literally physically melt the rack if you don't have the right thermal management.
Yeah.
And the projection for where this is heading is just mind-blowing. The current prevailing trends point to a nonlinear ramp-up towards 4,000 new hyperscale AI data centers globally by the year 2030.
Which is a staggering number.
4,000 of these massive factories.
Yeah, when you look at that number, 4,000 hyperscale facilities in just a few years, it really contextualizes the panic we're seeing in the market. The infrastructure blueprints we're analyzing explicitly compare today's data center operators to the early Bitcoin miners.
Oh, that's a great comparison. It's a gold rush.
It's an absolute gold rush. And in a gold rush, the most critical business metric isn't necessarily having the most elegant code.
Right.
It's how fast you can get your pickaxes into the dirt.
Yeah.
So time to deploy is becoming the single most critical business KPI for these tech giants.
I was actually thinking about this earlier. Imagine trying to assemble a Formula One car, but the race has already started.
Oh, that's good. Yeah.
The other cars are already on the track. If you are using outdated legacy IT tools, typing in manual command lines, waiting weeks for network provisioning to build a modern AI data center, you are essentially losing the race before you even leave the pit stop. Without a unified software platform that can rapidly provision and manage all this hardware simultaneously, the delays in getting your GPUs online are going to absolutely crush your return on investment.
You're spot on. An idle GPU is a massive financial liability. That's where this vertical integration becomes a game changer.
Yeah.
You need a platform that streamlines everything from day zero provisioning, which is just getting the bare metal to turn on and talk to the network.
Right, the absolute basics.
Yeah, exactly. From that, all the way to day two operations, like managing that massive thermal footprint using open standards like Redfish endpoint collection.
Which brings us to the actual foundation of this AI factory. To win that race, you need a track. And before you can run the AI, you have to build the physical and virtual house it lives in. In the NeoCloud architecture, they divide the underlying infrastructure into these structural entities called shards.
Shards, right.
So you might have a north, south, east, and west shard.
Right. And a shard isn't just a physical cluster of servers. It's a conceptual boundary. It represents an independent control plane.
Okay, so it's logical as well as physical.
Yes. It's a way to isolate and manage resources, often based on geographical boundaries for latency or for strict multi-tenancy.
Ah.
So one shard might service all of your European AI queries, another services Asia. Or if you're a massive defense contractor, you might have entirely different shards for different security clearances.
And the way they actually build these control plane shards is where we start seeing the hypervisor magic. They don't just run the control plane directly on a bare piece of metal.
No, that would be too rigid.
Right. They host it as a virtual machine. So, for example, they use an AMD physical server, and they install a CentOS 10 KVM hypervisor on it. And then inside that hypervisor, they run Ubuntu 22.04 LTS as the actual operating system for the control plane.
Yeah, let's break down exactly why they do that, because the hypervisor is really the unsung hero of modern computing.
I feel like a lot of people hear that word, but don't quite grasp what it's doing.
Totally. A hypervisor, conceptually, is a piece of software that sits directly on the physical hardware, the bare metal, and its entire job is to lie to the operating systems above it.
To lie to them.
Basically, yeah. It takes the physical CPU, the physical RAM, and it mathematically chops it up into isolated virtual slices.
So it's basically a hardware traffic cop. It tells the Ubuntu operating system, yes, you have your own dedicated computer, when in reality, it's just sharing a fraction of the AMD chip.
Exactly. It abstracts the hardware. This allows you to run multiple completely isolated control planes on a single massive server, which is highly efficient.
Right.
Though, it's worth noting, in a real enterprise deployment, you would never put all your control plane shards on a single physical hypervisor.
Because of a single point of failure.
Exactly. You'd split them across multiple physical racks so that if one power supply blows out, you don't lose your entire global brain.
Right. Redundancy is key. But once that hypervisor foundation is conceptually laid out, we hit what I think is the most critical physical bottleneck in this entire architecture.
Oh, the storage.
Yes. It's what I'd call the golden rule of storage for an AI cloud. And the rule is your virtual machine endpoints, specifically your QCLW images, must, without exception, be stored on NVMe drive pools.
It is entirely non-negotiable. And for those who might not spend their days in the IT trenches, a QCLW image, which stands for QEMU, copy on write, is basically a frozen snapshot of an entire computer.
Okay.
It's a single file that contains the operating system, the installed applications, the user settings, everything.
So it's freeze-dried compute.
That's a great way to put it, yeah. And when the system needs to spin up a new virtual machine, it has to fetch that massive QCLW file, thaw it out, and boot it up.
And doing that on old-school SAS or SATA spinning hard drives is apparently a massive disaster.
Oh, yeah.
In the architecture notes, it's literally referred to as bad news bears if you try to use older, slower, cold storage for those primary hot images.
It's bad news bears because of the orchestration layer sitting above it, which is Kubernetes.
Okay, right.
Kubernetes is highly, highly temperamental about storage timeouts. Using spinning SATA drives for a Kubernetes deployment is like a Michelin star chef that asks Kubernetes, yelling for ingredients from a waiter who has a broken leg.
And the chef works in milliseconds.
Precisely. The chef expects the truffles the exact microsecond he asks for them. If the waiter, the SATA drive, takes 10 seconds to physically spin a magnetic platter and fetch that QCLW image, the chef doesn't just wait patiently.
He flips the table.
He throws the whole meal in the trash. Kubernetes will literally time out, the virtual machine instantiation will fail, and it will throw cascading error codes across your entire cluster.
So you have to use NVMe, non-volatile memory express, because NVMe drives plug directly into the motherboard's PCIe bus. There are no cables, no spinning disks.
Yeah.
It's just pure instantaneous electrical bandwidth. It's the waiter sprinting at the speed of light.
Which is why the golden rule exists. Now, you still use those cheaper, slower SAS and SATA drives, but you use them for your cold storage.
Okay, like archives?
Yeah, your OS repository area.
Mm.
Things like ISO installation files that you only need to mount once a year. But the hot, active, freeze-dried computers, those have to live on the NVMe pools.
And managing those NVMe pools has historically been a nightmare of manual coding, but the architecture highlights this UI tool called Cockpit that sits in the hypervisor.
Yeah, Cockpit is fantastic.
It completely replaces the clunky old remote desktop protocols and command line text editors.
This is a huge leap forward for the time to deploy KPI we talked about earlier. With tools like Cockpit, a systems administrator isn't forced to manually edit massive script files.
You don't have to worry about putting a semicolon in the wrong column and breaking the entire cloud.
Exactly.
But even with a great UI, they stress some very specific unforgiving mechanics for setting up that back-end storage, particularly regarding how the hypervisor mounts the drives when it turns on.
Right, the UADs.
Yes, they specifically mandate using the bulkhead command in Linux to find the UUID, the universally unique identifier, for each physical drive, rather than just assigning it a generic label like drive C or disk 2.
And if we connect this back to the real-world stakes, skipping that UUID step is how you get a multi-million-dollar AI rack completely taken offline.
Walk me through why. What happens if I just name it disk 2?
Well, when a physical server reboots, maybe for a firmware update or after a power flicker, the sequence in which the motherboard recognizes the hardware can shift.
Oh, really?
Yeah. The PCIe lanes initialize in a slightly different order. If you told your operating system, hey, your most critical AI databases are on disk 2, and the boot sequence happens to hand that disk 2 label to a tiny empty flash drive this time.
Oh, wow. The system gets completely confused.
It looks for the data, finds nothing, and panics.
It literally enters what Linux calls kernel panic or maintenance mode.
Yes.
It halts the entire boot process. The server goes dark.
Exactly. But a UUID is an indelible mathematical fingerprint burned into that specific physical NVMe drive. Okay. When you use the UUID in your boot files, the system says, I don't care what order these drives woke up in, I am looking for the drive with the exact fingerprint of 8T3ATB, and so on.
Right.
It guarantees the system finds the exact right hardware every single time.
Okay, that makes perfect sense. So we've got our super fast NVMe storage properly mounted with mathematical fingerprints so it never gets lost. We have our Ubuntu control planes running inside our hypervisor slices. The track is laid, the physical house is built. Now, how do we distribute the brain power? Because the control plane isn't actually doing the heavy AI math, right?
Correct. The control plane is just the brainstem. It manages things. To actually run the AI models, you need physical compute servers loaded with GPUs.
Okay.
And to manage those servers, we shift into the Kubernetes layer of the operation. Kubernetes is an open source container orchestration system.
Right.
Its job is to take dozens or hundreds of individual physical servers and make them act like one giant unified supercomputer.
And the architecture blueprints detail exactly how they import these bare metal servers into the Kubernetes cluster using a deployment tool called kubespray.
Yeah.
But what caught my eye was how rigid they were about the software versions. They didn't just say install kubespray. They said, you must install Python 3, and you must use kubespray version 2.27.0.
That rigidity is the hallmark of enterprise infrastructure, and it comes down to a concept called dependency hell.
Dependency hell.
Yeah. In the consumer world, you always want the newest app update, right?
Right. I hit update on my phone without thinking about it.
Exactly. But in the enterprise world, an unexpected update is terrifying.
Because it might break the entire chain.
Exactly. Version 2.27.0 matches the exact tested, verified platform support profile for the rest of their networking and storage stack.
Like I see.
If an admin goes rogue and downloads version 2.28.0 because it has a shiny new feature, it might handle storage timeouts differently. Suddenly, the NVMe drives aren't talking to the hypervisor correctly.
The Kubernetes chef drops the truffles.
Right. The chef drops the truffles, and your AI factory grinds to a halt. Version locking is a strict survival mechanism.
And the security around actually adding a physical server to this cluster is intense. You can't just click an add button.
No.
It relies on a meticulous cryptographic handshake. You have to generate certificate authority data, client server data, and client key data on the node, and physically paste those cryptographic strings into the developer console.
It is a completely zero-trust environment.
Right.
The control plane refuses to give orders to a physical server unless that server proves, mathematically, that it belongs to the organization.
And speaking of trust and authority, there is a fascinating division of human roles built into this system.
Oh, this is a great point.
If you log into the console using the default system admin account, the God mode account, you actually cannot instantiate a virtual machine or run an AI workload. The button is physically grayed out or missing.
Which seems completely counterintuitive. The admin is supposed to have the keys to the kingdom.
Right. I was staring at this going, why would you lock out the admin? But it's brilliant. The infrastructure admin is only allowed to manage the switches, the storage, and the hardware health. To actually spin up a workload, you have to log in as a designated local user or an LDAP user.
Right, an LDAP, for those unfamiliar, is essentially the digital centralized guest list for an enterprise. You have to be an LDAP user explicitly assigned to a specific project.
It's the ultimate expression of multi-tenancy and the principle of least privilege.
Absolutely. The person swapping out a dead hard drive at 3 a.m. shouldn't have access to launch or view workloads in a highly classified corporate AI project.
Right.
It completely separates the infrastructure layer from the application layer.
Now, when it comes to the hardware actually running those applications, the blueprint heavily features NVIDIA GPUs, specifically the massive H100s.
Right.
But there is a very deliberate strategic move mentioned in the architecture. They are actively building support into the Kubernetes layer for a framework called HAMI or HAMI.
This is perhaps the most important business decision in the entire blueprint. Oh, absolutely. HAMI is an open source framework for advanced GPU slicing and virtualization.
Yeah.
But its real power is hardware agnosticism.
The holy grail, avoiding vendor lock-in.
Precisely. Right now, NVIDIA has a massive, almost monopolistic moat because of their CUDA software platform. The whole industry defaults to NVIDIA.
Yeah, everyone does.
But a cloud provider like Supermicro has to ensure their customers have a choice. By integrating frameworks like HAMI at the Kubernetes level, the control plane can seamlessly issue commands to NVIDIA chips, but it can also talk natively to AMD's MI300 series accelerators or Intel's Gaudi systems.
So if I'm an enterprise buying thousands of chips and NVIDIA suddenly doubles their prices, or they have a 2-year supply chain backlog,
What happens?
I can pivot my entire data center to AMD Silicon, and my software developers won't even notice the difference. The platform won't hold me back.
That is the goal.
Yeah.
But looking at this entire Kubernetes GPU sharing structure, it raises a really fascinating historical parallel.
I know exactly where you're going with this.
You do?
Yeah. In the blueprints, the presenter makes a casual comparison that really stopped me in my tracks. He's talking about this futuristic, cutting-edge, mathematically perfect GPU tenant cloud, and he compares it to his early days working on IBM 40631 mainframes in the 1970s.
Yes.
And I have to push back on this a little bit. Wait a second, is all this space-age AI infrastructure fundamentally just reinventing 1970s mainframe timesharing? Are we literally just doing the exact same thing, but with liquid cooling and a sleeker UI?
It is a brilliant observation, and the answer is, well, basically yes.
Really?
Yeah, but it's not that we are regressing. It's that computing architecture constantly swings like a pendulum between decentralized and centralized models, and that pendulum is almost entirely driven by the cost of the underlying resources.
Okay, walk me through the physics of that pendulum.
Think about the 1970s. A mainframe computer was the size of a room and cost millions of dollars.
Right.
No single department, let alone an individual human, could afford one. So you had no choice but to centralize the compute power in a massive climate-controlled facility. Hundreds of users accessed it via dumb terminals, basically keyboards and screens, with no actual brain inside them. The mainframe rapidly sliced up its processing time, sharing it among everyone.
And then the 80s and 90s happen, silicon gets cheap.
Exactly.
We figure out how to put a processor in a plastic box on a desk. We decentralize.
Exactly. The personal computer revolution. Everyone gets their own brain. You don't need the mainframe anymore. But now look at the physical realities of the AI boom.
Okay.
An 8-way NVIDIA H100 server rack costs hundreds of thousands of dollars. It draws so much electricity it requires specialized liquid cooling just to prevent a fire.
We are right back to a resource that is far too expensive, too hot, and too complex for individuals or even individual departments to own.
The GPU is the new mainframe. We are centralizing again out of sheer economic necessity. The NeoCloud, or GPU tenant cloud, is just a 21st century mainframe, and our software developers are just time-sharing those massive GPU arrays using web browsers instead of green-screen dumb terminals.
Wow.
The pendulum has swung all the way back.
That is wild. The technology is light years ahead, but the fundamental economic model is identical to 50 years ago.
Yeah.
Okay, so let's look at the people actually sitting at those modern dumb terminals. We've built this incredibly complex, heavy industry backend, the NVMe pools mathematically mapped with UUIDs, hypervisor shards, Kubernetes, cryptographic handshakes. What does the actual software developers see when they log in?
Here is where the magic of the abstraction layer truly shines. The developer doesn't see any of that plumbing.
Not a bit of it.
No, they don't know what a UEID is, and they shouldn't have to.
Yeah.
Log into a clean, modern web interface.
And this is where that frictionless feeling we talked about at the beginning comes from, because the speed is just incredible. The infrastructure admin has already set up what they call flavors in the UI. I love this term. It's basically pre-configured t-shirt sizes for compute power.
Right, small, medium, large.
Yeah, so a developer clicks a drop-down and chooses a flavor that is 4-core with 8 gigabytes of memory, or maybe a beefier flavor that's 8-core with 16 gigabytes.
And then, with literally a single click, they deploy a full virtual machine. In the architecture demo, we see a developer seamlessly click down a list, deploying a Windows 11 host, an Ubuntu host, a CentOS host, and a Rocky Linux host. Just boom, boom, boom.
And within moments, those VMs shift from building to a ready state. The developer just clicks a VNs console link right there in the browser, and they are instantly dropped into a live Ubuntu terminal.
It's that fast.
They do a quick ping to Google's DNS at 8.8.8.8 to prove the external network is live, and then they run an apt-get update command to pull down software packages from the internet. It works flawlessly.
The abstraction is complete. All that complex IP address floating, the storage mapping, the Kubernetes cluster management, it is entirely hidden. The developer just hits submit, and they have a working environment in 30 seconds.
That's incredible.
But standard virtual machines are just table stakes. The real prize of the AI factory is the AI containers.
Absolutely. The exact same one-click philosophy applies to deploying complex AI development environments. Say a data scientist wants to start training a model. They select an AI flavor, a profile that assigns, let's say, 1 or 3 physical GPUs directly to their container. They punch in a password for their Jupyter notebook, and they hit submit.
And a Jupyter notebook, for context, is essentially an interactive digital diary where data scientists write code, run equations, and visualize data in real time. It's the standard workbench for AI.
Right. So they hit submit, the system queues it up, initializes the massive container image pool, and within minutes, they have a secure live endpoint. They click the link, and they are dropped straight into that Jupyter notebook ready to write code.
If we analyze the pure business value of this UI abstraction, it is immense. Think about the legacy IT model we discussed earlier.
Yeah.
A machine learning engineer's time is incredibly expensive. In a traditional setup, they might decide they need an environment to test a new model.
Okay.
They submit a ticket to IT. They wait 2 weeks for IT to provision a server, map the storage, figure out the Linux dependencies, manually install the very finicky NVIDIA CEDA drivers, and configure the firewalls.
By which point, the data scientist has lost their train of thought, or worse, the market has moved on entirely.
Exactly. By removing all of that friction and reducing a 2-week IT ordeal to a single click, you are directly accelerating the enterprise's ability to innovate.
You are maximizing the ROI on that incredibly expensive human talent.
Yes.
And the blueprints actually walk through a live demo of what you can do once that one-click environment is set up. They instantiate a local AI GPU inference deployment using a gamma model.
Right.
And what's crucial here is that this isn't reaching out to OpenAI or Google over the public internet. It is all running locally, contained entirely on that single deployed GPU slice inside their own rack.
Total data privacy.
Exactly. And they test it with a conversational chat interface right in the dashboard. They ask it 2 specific questions to test its contextual retrieval.
Do you remember what they were?
Yeah, first they type, "Who is Elon Musk?" And instantly, the local model sheets back a detailed, accurate bio. It mentions he was born in South Africa, early days at Zip2 and PayPal, CEO of Tesla and SpaceX, founding Neuralink, and acquiring Twitter in 2022.
It proves the model has its foundational knowledge intact.
Right. Then, to test geographical context, because the architect in the demo happens to be based in Arizona, he asks the model, "Where is Tucson?"
Okay.
And the model perfectly places it in the Sonoran Desert, highlighting its specific southwestern location and even detailing its deep Mexican and Mediterranean culinary influences.
Which is brilliant proof of concept.
Hmm.
It demonstrates that you can have world-class, nuanced AI inferencing completely walled off inside your own corporate infrastructure, deployed by a developer in minutes.
It's amazing to think that all that knowledge, all that semantic capability is being processed locally on a server you just spun up with one click.
Yeah.
But that brings us to the final and undoubtedly the most mathematically complex piece of this entire puzzle.
The networking.
Exactly. Exposing these frictionless tools to your developers is great. But how do you secure this neocloud? If you have multiple tenants, say the HR department and the R&D department, sharing the same physical GPUs,
Right.
how do you mathematically guarantee that tenant A can't see what tenant B is doing?
This is where we have to dive into the deep end of the network plumbing, the air gapping, and the intense security protocols.
Oh, okay, take me into the deep end.
The physical foundation of this relies on a specific layout of network cables and switches called a leaf and spine architecture. Supermicro relies heavily on this.
Okay, I read that term in the blueprints, but I need you to help me visualize it. What does a leaf and spine physical network actually look like compared to a normal office network?
Right, in a traditional office, networks are built like a tree.
Hmm.
You have a main router at the trunk, which splits to big switches on each floor, which split to smaller switches in each room.
That makes sense.
But a tree topology is terrible for AI, because if a server on a small branch wants to talk to a server on another small branch, the data has to travel all the way down to the trunk and back up. It creates massive traffic jams.
So what is leaf and spine?
Leaf and spine is a mesh.
Hmm.
Imagine the spine switches as the massive, high-speed central highways of your data center.
Okay.
The leaf switches are the local on-ramps that connect directly to the racks of servers. The absolute rule of this architecture is that every single leaf switch connects directly to every single spine switch.
Wow. Okay, so it's a massive crisscross of cables.
It's an incredibly dense web. This
Yeah.
means that no matter which server you are on, you are exactly one hop away from any other server in the data center.
Oh, I see.
It guarantees ultra-low latency, which is exactly what a distributed Kubernetes cluster needs to function without timing out.
Okay, so we have this massive ultra-fast mesh network. But if everything is connected to everything, how do you isolate the tenants? How do you create those shards we talked about earlier?
That is handled mathematically through VLAN plumbing, virtual local area networks.
Okay.
Remember our shards? North, south, east, west?
Yeah.
They are strictly separated by VLAN tags at the switch level. In the architectural configuration we're reviewing, the north shard is assigned VLAN 901, south is 902, east is 903, and west is 904.
And there was a management one too, right?
Yes, there's also a native management VLAN 671, which allows the infrastructure admins to securely SSH into the bare metal servers for emergency maintenance without touching the tenant data.
I was trying to conceptualize this, and the best analogy I could come up with is a high-security apartment building.
Okay, let's hear it.
Everyone in the building shares the exact same physical foundation. You know, the concrete, the elevator shafts, the plumbing. The spine and leaf switches are the concrete.
Right?
But the VLANs act as invisible mathematical concrete walls.
That's a great starting point, but let's push the analogy further into how it actually works. It's not just a wall, it's a cryptographic lock on the elevator doors.
Yeah.
Every single packet of data that leaves the server gets stamped with a numerical tag. If a packet leaves the server in the north shard, it gets stamped with a 901.
Okay.
When it hits the physical switch, the switch looks at the tag. If it says 901, the switch will literally refuse to send it down a wire that leads to a 902 server.
So a tenant in apartment 901 can't even see the door to apartment 902, let alone knock on it. They share the same physical cable, but the switch blinds them to each other.
Exactly. That is how true multi-tenancy works on shared hardware.
Wow.
But if they are entirely isolated, how do they connect to the internet to download their GitHub code or update their software?
Right. They still need the outside world.
To route that traffic safely to the outside world, you need a highly intelligent gatekeeper. In this architecture, they deploy an OpenSense WireGuard server on a multi-NIC physical machine.
Multi-NIC meaning a machine with multiple network interface cards, multiple physical ports to plug cables into.
All right, and OpenSense is a powerful open-source firewall platform. In the enterprise context, this OpenSense server sits at the edge of the network and handles NAT, network address translation.
Okay, define NAT for us. What is the firewall actually translating?
Inside your VLAN apartment building, your Kubernetes virtual machines have internal, private IP addresses. They are meaningless to the outside world.
Right.
If that VM tries to ask Google for a file, Google won't know how to send it back. NAT is the process where the OpenSense firewall takes the internal request, slaps the corporation's official public IP address on it, talks to Google, gets the file, and then routes it back to the specific internal VM that asked for it.
It's the mailroom of the apartment building?
Exactly.
It takes packages addressed to apartment 901 and relabels them with the street address of the building so the post office can handle them.
That's it exactly. And beyond NAT, this OpenSense server handles secure VPN access for remote developers working from home, and it enforces incredibly strict firewall policies between every single VLAN.
Now, looking at the documentation, setting this all up is apparently a massive migraine-inducing headache if you only come from a traditional corporate IT background.
Oh, it is, because the paradigm of how a network exists has completely shifted underneath them.
How so?
A traditional network engineer is used to dealing with physical ports on a wall and static IP routing. I plug cable A into port B, but Kubernetes completely virtualizes the network.
Right.
It creates a dynamic, ever-shifting web of electrical connections between virtual ports or vPorts and virtual NICs or VNets.
And all of those virtual imaginary connections have to map flawlessly down to the actual physical VLAN tags on the leaf switches. If the software and the hardware aren't perfectly aligned, the data drops into a black hole.
Precisely. And the blueprints spend a lot of time emphasizing a specific Kubernetes command to prevent this, kubectl get node.
Okay.
This command tells you the exact assigned role of every physical server in your cluster. If the output says scheduling disabled, that node is a pure control plane. It's the brainstem.
Right.
It is managing the traffic, but it is explicitly forbidden from hosting developer virtual machines or AI containers. But if the role column is empty, that indicates the node is a pure worker. It's the muscle.
Why does that distinction matter so fundamentally for the network plumbing?
Because it dictates how the bridge interfaces, specifically what they call BA1 in their Linux netplan configuration, are tagged.
Ah.
If an admin messes up the netplan file and doesn't configure the bridge and the VLAN tag correctly on a specific worker node, think about what happens.
Good developer clicks their one-click UI.
Right. The developer clicks Deploy PyTorch. Kubernetes looks at the cluster, finds an empty spot of worker node 7, and instantiates the virtual machine. But because worker node 7's bridge isn't tagged correctly to talk to the OpenSense mailroom, that VM is completely stranded.
It spins up, the developer logs in, but it has no internet. It can't ping 8.8.8.8.
The invisible concrete walls of our apartment building suddenly trap the tenant inside a room with no doors and no windows.
Oh, man.
The application breaks, the AI model can't access its training data, and the whole system grinds to a halt. The physical switch layer, the hypervisor bridge layer, and the Kubernetes orchestration layer must be perfectly mathematically synchronized.
And the stakes for getting that synchronization right, for building those invisible walls perfectly, are incredibly high.
Unbelievably high.
The architectural review mentions specific high-security use cases that demand this rigorous level of air gapping. You might have one tenant, let's say a major pharmaceutical company, running a cluster that is processing highly sensitive healthcare DNA inferencing data. And right next to it, sharing the exact same physical spine switch, you might have an unclassified government cluster operating alongside a highly classified government SCIF, a sensitive compartmented information facility that is running quantum cryptography models.
That's a terrifying mix if it's not secure.
You absolutely cannot afford a single packet of data, a single line of text, leaking from the quantum crypto SCIF into the unclassified cluster or the DNA database, even though their mathematical equations are being processed by GPUs sitting literally 1 inch away from each other in the same server rack.
Which is exactly why the meticulously configured OpenSense firewalls and the strict mathematical VLAN tagging at the leaf and spine switches are the absolute bedrock of the entire NeoCloud concept.
Right.
Without that ironclad security, the frictionless developer abstraction layer is useless. No enterprise will trust it.
So we have covered an immense amount of ground today on how you actually build an AI factory. We started at the very bottom, looking at the unforgiving physics of storage, why ultra-fast NVMe and mathematical UUID fingerprints are the absolute lifeline for Kubernetes QCRW images. We moved up into the hypervisors and the control planes, exploring the strict cryptographic handshakes and the hardware agnosticism required to import clusters and avoid vendor lock-in.
We then explored the economic necessity of the centralized pendulum swing, how the modern GPU cloud is really just a sleek return to 1970s mainframe timesharing.
Yeah, that blew my mind.
And we saw how that incredible developer abstraction layer allows complex AI environments to be summoned in 30 seconds, skipping weeks of IT provisioning.
And we wrapped it up by looking at the invisible concrete walls, the meticulous leaf and spine mesh networks, and OpenSense firewalls that secure the entire architecture for true zero-trust enterprise multi-tenancy.
Yeah.
I think the big takeaway for me, and hopefully for the listeners, is a profound appreciation. The next time you open a browser, type a prompt, and a chatbot instantly answers you, you now understand the immense coordinated architectural ballet of hypervisors, shards, VLAN tags, and NVMe drives that are violently crunching math behind the screen to deliver that ethereal text.
It truly is a marvel of modern engineering. We are orchestrating thousands of physical and virtual moving parts in milliseconds, completely seamlessly.
It is a marvel. But I want to leave everyone with one final, slightly chilling thought that jumped out at me from the very end of the architectural blueprints.
Oh, the power issue.
Yeah. During the internal presentation, the architect casually mentions a massive problem they ran into while building this demo lab. They actually ran out of power.
Yes, the thermal and electrical draw of those new NVIDIA H100 GPU servers became a hard physical burden on the facility.
They hit a hard electrical ceiling. The building physically could not provide enough electricity to keep the racks running, and they were forced to pack up and physically relocate their entire lab to a new, specialized liquid-cooled facility just to keep the demos online.
Wow.
So here is the question to mull over tonight. If a single AI demo lab, built by the absolute best experts in the world, is hitting a hard electrical ceiling today, what exactly is going to happen to the global power grid when those 4,000 massive AI data centers we talked about go online by 2030? Can our physical infrastructure, our dams, our power plants, our transmission lines actually sustain our digital ambition?
It is the multi-trillion-dollar question of the decade.
Yeah.
The software orchestration is ready. The hardware silicon is ready. But the copper wire in the power grid, that might be the ultimate unbreakable bottleneck for the AI revolution.
Ethereal and weightless, right up until the likes flicker. We'll leave it there for today. Thanks for diving deep with us.